Let's see this question. Range some query mutable. So in the question they have given us a array number of integers and you have to handle these multiple queries. Either you have to update a value in the given integer array, or you have to find the sum of number between left and right inclusive, where left is less than right. So given at some point you have to find the sum of all the integers between left and right, but they keep updating the values of integers in the number, so you cannot use the prefix strict. So the naive solution would look something like this. You will have a class level variable where you assign the value of the given array to that, and when they ask me to update a value in the array, I will set the value of that particular index to be whatever it has to be updated to. And finally, for getting the sum of all the numbers between left and right, I can have a sum variable and I can iterate from left to right. So as they have said that both has to be inclusive, so I will initialize from left but also have until the value is right, and I'll add all that values to the sum of I, then finally return the sum. So as you can see, this will work on the smaller cases. This is giving me correct answer, so it will pass some of the test cases for me as well. But the 15 of the 16 test cases have passed. That doesn't mean that for just one test case you should not do this work, but the segment tree is a standard data structure which has to be learned, so there are other problems as well which can be solved with the segment tree. As you can see, the constraint, the length of the integer array can be up to 10 power 4, and the number of queries will be also 10 power 4. So in worst case they will ask me from left 0 to full num dot length, which is 10 power 4 in each query. So in that case the number of operation is going to be 10 power 4 multiplied by 10 power 4, which is 10 power 8, which is out of the time limit for the question in the lead code. And the time complexity as well is order n square, since in each query you are iterating for entire array. So that is n queries and n iteration in each query, that is n square. So we can optimize it with segment tree. So now let's see what segment tree is and how the operation on that works, then we'll come back to this question and use the segment tree to solve it. Now let's see how segment trees are constructed and how a query can be performed in that. There is update as well on the segment tree. So let's say I am given this array and I have to construct the segment tree for that. So all the values in the given array is going to be the leaf, so they will be at the bottom of the tree, but we start our construction from the top. And this is how a segment tree node is going to be look like. It will have the sum will represent whatever range that node of the segment tree is representing, what is the sum of all that leaf nodes. Then there will be range, that is it will represent what range of number in the leaves that node is representing. So this will get clear with example. Then there is going to be left child and right child in each node. So we will start from the top, and at the top we don't know what is the value of sum is right now. We don't know what is left and right child are, but we know what range it is going to represent. So it will represent the entire array. So we initialize the range, but we left out the sum and left and right child. Then we'll make a recursive call on the left and right side both, but we start with the left side. So this is the code that we will use while making the segment tree. And in both left and right half, we'll divide the range in two. One is left half, one is right half. So left half is 0 to 3. And then again we'll recurse it as long as the range is not a single number, that is it is not from x to x. That means range which is from 1 to 1 is a single number. So that's how long we are going to recurse. So we again call the left half of the range. So for 0 to 3, left half is 0 to 1. Then again we call the left side. Now finally we are at some point where the range that we have called on the left side is going to be 0 to 0, and that point we will convert that array to a node. So it will be a leaf node for the segment tree. It will have some, since we know what the sum is going to be a single number, that is the number what it was. So we initialize the sum as well. The left and right child are going to be null, and the range is going to be that single 0 to 0. And once the leaf node is constructed, we are going to return that. So the return value here is going to be that leaf node, and that will become the left child for this particular node. Similarly, we do for the right side. The range is 1 to 1 and sum is 1, and this will be written, and that will become the right child for this particular node. So now first time we are returning back from the left and the right child, since for the leaf node it was null and null. So here we have the sum calculation possible. So the new segment tree node that we are going to create, it has these particular values. The sum is going to be sum of the left and right nodes value. The left child is going to be the node that has returned from left, and similarly the right child is going to be the node that has returned from right, and the range is going to be as it is. So range we know for each node from the call that it has made from. So that means the range is coming from the call, and the sum and the left and right node are going to be derived from the children call that it is going to make. As you can see, these values will be populated in these particular locations. Then we will return this node, non-leaf node, which will become the left node for this particular node, which is representing the range from 0 to 3. Still we cannot calculate the sum right now, we only know the left child. So we will do this for this right subtree entirely as well. So as you can see, the range it represents is 2 to 3. The sum is the sum of the leaf node 5 and 8. So this will have sum as 8, and finally this is going to be returned for 0 to 3 range node, and the sum value for this going to be sum of the left and right node, not the sum of entire subtree. So it won't have sum of 3 2 1 8 5 3, because that will double the value, since this is already the sum of these two nodes. So for this node we are going to have sum of only its direct child nodes, which is 8 plus 3, which is 11. So this will finish this recursive call for the left child of the root node, and this will become the left node for the root node. And similarly we are going to do for the entire right side. So I am directly changing it as we done for the left side. So this will finally have the value for the sum as 26 for the right half of the subtree. And then finally for the root node, we know the sum is going to be 26 plus 11. And now we can see how finding the sum of a subarray is going to help. But before that, let's see the implementation of construction of the segment tree. Now let's see the implementation of construction of segment tree. So segment node will look like it has a value which was sum in the example that we saw. It has the range it represent, and it has left and the right childs. So we have two constructor, the value and the range, because in some case left and right child are not going to be there, which is the leaf node, and the other case is when all the four values are there, value, range, left and the right node. So this is going to be a data class. It doesn't do any calculation, it's just going to hold the values. Now we see how the calculation for those values happen. So let's say I have the segment tree class. I have a constructor where I am just receiving an array, and I am doing a recursive call for build segment tree. I'm passing the array and the range at the top node, that is the root node, for 0 to n minus 1. So this range represents the entire array, and that was going to be converted to the root node. Finally, let's see the recursive implementation for the build segment tree. It has the array and the range. It is converting node 2. So the terminating case is when the range is an element, as we saw in the slides, that if it is a single element, it is going to be the leaf node, and it doesn't need any more calculation for the left and the right child. The sum is going to be for that is the number that is present in the array at that index, and the range is going to be a single element range that is from x to x, and we'll return that as a segment node, which is going to be a leaf node. Now the recursive call for the left and the right side. So I'm calling the build segment tree for the left side. For the left side, the array I'm passing as it is, and the range is the left half. So we'll see in the implementation for the range class how the left half, right half are calculated, and how we check if it is a single element. So this is simple enough. If start is equals to end, that is a single element, uh, we'll see left half and right half, although we have seen in the binary search previously in the range class. I reutilize the range class everywhere, so it is very useful to not do the calculation for the left half, right half, and every range related thing here. Instead, better to make a class here and reuse that class in other questions as well. So for example, in binary search we did, here we are using, and also in the merge sort it can also be used. But let's see how the recursive calls work here. So for the left and right side, I have done the recursive call, and whatever nodes they have constructed, I am storing them in the left and the right side. And finally, to create this particular node, the sum is going to be whatever is the sum of the value on the left and the right side, same way as we see in the slides. Range is calculated in the parent. So as you see for the left node, I am calculating the left half here and passing it. So parent does the calculation for the range for me, so I can directly use in the constructor here. And finally, the left child and right child is going to be whatever the left recursive call and the right recursive call has calculated for me. Now let's see how finding the sum of a subarray in the segment tree works. So let's say I've got a query which is find the sum of all the numbers between range 3 to 6. We start with the root node and we recursively call the left and the right child, but we prune at some points. So let's see how that works. So we recursively call for the left and the right child here, and checks with the range that this particular node represent. So if it has an intersection, so the range class can have a method which tells whether two ranges do intersect or not. So this is what we are going to use, and we check if the node and the query range, if they intersect, then we are going to call the left and the right side. Otherwise, if they are independent, we are not going to make any recursion call. So let's see in this example how this proceeds, and this will explain more how the recursive call for finding the sum in the given range works. We'll again call the left and the right side. Now see this, at this point there are some non-overlaps. So if you see from 0 to 1, it doesn't overlap with the query range at all. That means none of the element in the array which are the child of this particular node are going to be in our answer. So at this point we can prune this part. That means we can return it 0 because array element within this range are going to be part of my answer. And another optimization we can do, if a range is completely within the query range, that means 3 to 6 completely envelopes the range for this particular node. So 3 to 6 have 4 5 completely covered. That means all nodes within this particular nodes are going to be in my answer. That means all the leaf nodes that are under this node are going to be in my answer. So I don't have to recursively go down them. That means the sum that this node has is going to be in my answer. So I don't recursively call it, I'll just return the sum for this node from here. So 11 is going to be returned from there. And for other two nodes, which is 2 and 3 and 6 and 7, they are not independent of the query range, but they are also not completely enveloped. So in this case, we are going to do further recursive call for both the left and the right child. We'll do the recursive call for left and the right side. So the leaf nodes which are completely outside are this and this. So finally the leaf node are going to be either completely outside of the query range or completely within. Since they are a single number, they can't have a overlap, partial cover and partial not cover. Nodes which are completely outside, they are going to return 0, and the nodes which are completely within the range, they are going to return their sum. So from here 3 is returned, from here 6 is returned, and 11 was always returning from here. So from here we will return the sum of the left and the right side. So from here we have returning 7, and from the left side we are returning 3, and finally 17 and 3, it will going to be 20. And if you remember the question, it was from 3 to 6. So if you see 3 4 5 and 6, the sum of these values is also 20. 7 3 10 and 6 4 10, the sum is 20, which is what we are getting from the answer. So if you notice here, we have not traversed the entire leaf node, so the number of operations are not order n, but they are height of the tree, and the height of tree is going to be log n. Why? Because at each level we are reducing the number of nodes to half. So if you see here, we have 8 nodes, the level above 4, then 2, and then 1. And in general, anywhere when we have n nodes, at the level above it, the parent level, it is going to be n by 2 nodes. So in general, the time complexity for finding subarrays range sum is going to be order log n. So now let's see the implementation of rest of the methods. We saw building of the segment tree. We also have update a single index, and we also have a query for sum of the numbers from left to right. So these are the just the wrapper methods which we expose in public, and we have a private method which recursively call on the segment tree. So how this work, we call for sum of numbers between this range, and we also have the current root node. So we'll recursively call on the tree here. We start with the root node. So the conditions that we saw, if a range is completely outside of the query range, then we are going to return 0. And similarly, if the range in the query completely covers the range of this node, then we can simply return the value at the current node. And finally, if both of these conditions are not satisfied, that means there's a partial overlap, so we will recursively call left and the right side, and whatever the return value we get from them, we are going to sum it up and return as the answer for the query. That's the implementation for querying. I have still not explained the implementation for the range related methods. We'll just see them in a second. But before that, we have the update method. So if we want to update a value at index in the array, so this is how we'll do. We again create a recursive method update. We have index value and the current node, which will recursively going to call the children's. So the conditions here are, if index which we want to update is completely outside the range for this node, so if that index is in the range and not to that means that index is not in this range, so we are going to return, we don't have to do anything. If the current range is an element, that means we are at a leaf node, and this leaf node is actually the index that we want to update, so we change the value of that node to the new value and return there, because since it's a leaf node, we don't need to recursively call left and the right side. But in the case other than these two, we'll have to call recursively left and the right side. So to do that, we'll call for the left side, and for the right side, the current is a segment node, so it has left and the right child. If it is not an element, that means it's an internal node, so we can call the left node and the right node on that, and we'll do the recursively call for update for every node. And once we have updated the left and the right child recursively, after that, that is a head recursion. That means after you have made the recursive call, you are going to update the current node. So why is that? Because before updating the current node, you have to update the children's, because children's are independent nodes to their parent, but the parent's value is calculated based on the children. So that's why I'm doing the head recursion here. And finally, once the recursions are done, so the current value can be updated the same way that we did at the time of construction. So the value for the current node is left values node and the right values node sum. This will do for the update. As you see, the recursive methods for both update and query I have kept private, because I don't want to expose the internal structure of the segment tree for the client. So the client can only ask me to update a value at an index, and similarly it can only ask me for giving me sum from left to right, but not somewhere in between the tree. So I have kept those methods private. So finally, let's see the range class. So whatever calculation we need to do related to the range class, I have kept them in as method inside the range class to keep it as separation of concern. The range class is simple enough. Again, it has a start and an end. The mids formula is same as we saw previously, and a range is an element when start is equals to n. That means it's representing a single element. Index in range is again simple enough. If it is greater than start and it's less than end, that means it's within the range. Now this is important method. So is outside for other range, I want to calculate if these two ranges are independent or not. There are two cases when those ranges would be independent. One is which this class belongs to, so I'll call it this. That is also a standard practice in Java. And there is other range, so I just want to make a comparison if these two ranges are independent or not. The two cases, as I said, are going to be, one is this, when the other range end is before the start of current range. That means the other range is completely behind this current range. That is one case. The other case is when the other range is completely after the current range. When is that going to happen? When the other range start value is greater than this range end value. These are the two cases when the ranges are going to be independent. That's the only method I have used. I also needed if two ranges are intersecting or not. That can be simply enough derived from this. If they are not outside, that means they are intersecting. Where I have used that exactly? So if you see, I have checked here, if a range is outside the other range, then I am returning 0. If that is not the case, that means either it is covered. That case I have handled before that. And finally, when these two cases are not true, that means there is partial overlap. So this return condition, although not explicitly checked, but this is the condition where there is a partial overlap between the query range and the nodes range. So let's see the range cover method. So that is also we have used. That was the case when we wanted to prove that we know that the query range is completely enveloping the nodes range. That's when this method we have used. So if you see this, the range covered. So how that is done, how a other range is going to be completely within the current range? It is when the other range start point is after the current range start and other range end is before the current range end. That means the other range, the range that I'm querying for, is completely within the range for this class. And then finally for the left half, it's from start to the mid, and the right half of the range is from mid plus 1 to end. So this is the range class. It is very useful not only here, in other questions as well, but to start making it as a class. And that's all the methods we have used. Finally, I can use this segment tree and solve this problem. So since I have made all the methods that I am going to need, I can simply call them. So for initializing, I have initialized the segment tree object with number, so whatever array they have given. When the query is for update, I am simply passing the index to be updated and the new value. And finally, for the sum range, I want a sum of all the numbers between left to right. I'm querying it from left to right. And as we saw in the slides, for getting a query, a sum of numbers between left and right, I traverse the tree from top to bottom. The height of the tree is going to be log n, so the time complexity for this operation is log n. The update method, again, it is similar but even simpler than the query. So here also I am traveling from top to bottom in the tree, so the height of the tree is log n, so the time complexity for this operation as well is log n. And finally, for the construction, I am going to create a node for each element in the array, so the construction is order n for this operation.